Up till now, we've been talking about different ways to identify electrons on an element, a particular element on a periodic table. So if we're talking about hydrogen, it's actually really easy. We have our quantum numbers. We could do 1, 0, 0, 1/2. We have electron configuration. We draw the orbital as a dash, write the electron as an arrow. Or we have electron configuration where we write 1s1. All of which work very well. But this gets hard to do if you're talking about an element far down on the periodic table with a lot of electrons. Let's say we're talking about lead over here, number 82. You have to write 82 sets of these, or 82 of these, or 82 of these. It's really hard. And you have to memorize that mnemonic, right? The whole 1s, 2s, 3s, 4s, 2p, 3p, 4p, etc., that whole thing. I'm about to make that mnemonic obsolete and make your way of writing all of this so much easier. All you really need is a periodic table. The periodic table is the greatest cheat sheet there is. Let's think about writing some electron configurations. Hydrogen, we've already said, is 1s1. That's hydrogen. What if we talk about lithium, which is right here underneath hydrogen? Lithium has 3 electrons, and it's 1s2, 2s1. Let's talk about sodium, right underneath lithium. That's 11 electrons, and it's 1s2, 2s2, 2p6, 3s1. Notice what's happening here. They're all ending in s1. If I did potassium, it would also end in s1. Rubidium, cesium, francium, they would all end in s1. The periodic table is actually laid out according to electron configuration. Check it out. How many electrons can fit in an S? 2, right? See these? This area of the periodic table has 2 columns. All these guys will end with 1 electron in the S. All these guys will end with 2 electrons in the S. That's why there's 2 columns here, because there are 2 possibilities for electrons in the s orbital. Over here, this section of the periodic table, 1, 2, 3, 4, 5, 6. There are 6 columns here. What else is 6? The number of electrons in a p orbital. So all of these, this is called the p block. This is the s block. This is called the p block of the periodic table. And all the electron configurations will end here in p. Everything here will end with 1 electron in the p. Everything here will end with 2 electrons in the p. 3, 4, 5, and 6. Here in the middle, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Which orbital has 10 electrons? The D. These here, all of these electrons will end with, all of these orbital configurations will end with 1 electron in the D, 2 electrons in the D, 3, 4, 5. And down here, those are the F's. So you never need your mnemonic again. You can actually follow along on the periodic table. First comes the 1s, hydrogen and helium. Then comes the 2s. Then I'm going over here and I'm at the 2p. Then the next thing down I'm at the 3s. 1, 2, 3, the 3s. Here I'm at the 3p. Remember, p starts at 2, so if I'm counting down, it's 2, 3. And now I'm at the 3p. Here I'm at the 4s. 1, 2, 3, 4s. Now the d's. D's, remember, start at 3. So even though this is the 4s, this is the 3d. This one here is the 4p. Here's the 5s, the 4d, the 5p, the 6s, and oh look, that's where the f's start coming in, so after the 6s comes the 4f, then the 3, 4, 5d, 6p, 7s, 5f, 6d. I'm done. Done with known elements of the known universe. Well, actually, these days, we know some of these too. But that's why I stopped the mnemonic at 8s, because 8s is over here. So let's check this out. Let me erase all this. Okay, so let's check this out. Let's say I'm doing chlorine. I can tell you right now it's going to end at, here's the P section. It's going to end in the P's. It's going to end in 3p. That's the 3p row. And it's going to end with 1, 2, 3, 4, 5 electrons in that 3p row. So it's 1s2, 2s2, 2p6, 3s2, 3p5. Let me add that up. 2 plus 2 is 4, 4 plus 6 is 10, 10 plus 2 is 12, 12 plus 5 is 17. Chlorine's number 17. That's how I've been doing it so fast all this time, because I don't need the mnemonic. I look at the periodic table and I can tell you what the electron configuration is. Let's try another. Palladium. Right there. Okay, that's going to end at 4d, 1, 2, 3, 4, 5, 6, 7, 8. 4d8. So I just keep going until I get to 4d8. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d8. And if you add those all up, all those superscripts, you will indeed get to 46. 10, 20, 30, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46. 46. Now, knowing this, we can actually do an even easier version of electron configuration. This is called the noble gas configuration. Remember, the noble gases are these guys right here. And knowing what we know, they all end in P6, right? They all end with a filled shell. That's why noble gases don't react. Because the motivation for everything to react is to get a filled shell, and these guys already have filled shells. They end in P6, and that's what we want. So all those electrons that are not involved in a reaction, they're called inner shell electrons, we don't really care about them. As chemists, we're ignoring them because they really don't make a lot of difference in a reaction. The ones we care about are the valence electrons, the outer shell ones, the ones that are in layers that are not filled. So those are the ones that matter for the most when we write an electron configuration. So in a noble gas configuration, we're going to hide all those inner shell ones and just worry about the outer shell ones. Let me show you how to do that. Let's say we're talking about sodium, just again in the interest of being fairly short here. The electron configuration for sodium, remember, is 1s2, 2s2, 2p6, 3s2. Well, all this part, this is the filled part. These are the inner shell electrons, the ones that are all in filled shells. It's only these, the 3s2, that are not in filled shells. This is all filled. And if you look, this is the electron configuration of neon. 1s2, 2s2, 2p6. That's neon. So instead of writing this whole darn thing, all I really have to write is in brackets I write neon, and then I write the 3s2. That's why it's called the noble gas configuration, because always I write all the inner shell electrons simply by writing the noble gas, whose configuration is all of that. Has to be a noble gas, and it has to be in brackets. So now think about something way down here on the periodic table. Something like barium, which is number 56. The nearest noble gas without going over is xenon, number 54. And remember, I can't do the one over it, after it. I have to do the one before it. So, the nearest noble gas without going over is xenon. So if I'm writing nearest noble gas without going over is xenon, so I write xenon in brackets. This is where it's helpful to read the periodic table, because now I need to know what electrons I put after xenon. I'm in the S section, so I know I'm going to end in S. 1, 2, 3, 4, 5, 6. I'm in the 6s. 6s1, 6s2. So it's xenon 6x2, which is a heck of a lot easier than for saying 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2. Noble gas configuration is a lovely thing. Let's do another. Let's try lead, which is number 82. Okay, again, it's going to be xenon. Xenon. So now we're back here to the 6s, 6s2. Don't forget, here's where the F's come in. So 6s2, 4f14. Then we're all the way back to here. That's the 3, 4, 5d, 5d10. Then now we're over here in the P's, so that's 2p, 3p, 4p, 5p, 6p, 6p, 1, 2. And that's the noble gas configuration for lead. Remember, when you're doing this, the number in front of the S and the P is always going to be the same. The number in front of the D is always going to be 1 less than the number in front of the S and the P. And if you have an F, the number in front of the F is always going to be 2 less than the one in front of the S and the P. Because S's start with 1, P's start with 2, D's start with 3, and F's start with 4. And again, it all goes back to quantum numbers and what's allowed for quantum numbers. By the way, as long as we're talking about all this, I do want to tell you a couple of exceptions to electron configuration. The thing is, again, everything wants to be a noble gas. Everything wants to have filled shells, because that's the lowest in energy, and everything in the universe heads towards least energy. It is true that filled shells are lowest in energy, but it's also true that half-filled shells are lower in energy. So, where that manifests itself in electron configuration is here in the D4s. All of these guys that I've circled here, they end in the electron configuration D4. So chromium here, for example, if I were to do the noble gas configuration for chromium, according to the rules I've already taught you, it would be argon, then it would be 4s2, then it would be 3d4. But if you look up the electron configuration of chromium, it isn't actually that. And it's because the S's and the D's are really close in energy, and half filled is stable. So what chromium ends up doing is promoting one of the electrons from its S into its D so it can be half filled. So reality is not this. Reality is argon 4s1 3d5. That's true of all the D4s. They end up promoting one from their S to become D5s. That is equally true here of D9s. Okay? Something like silver will be krypton. There's the krypton. And then 1, 2, 3, 4, 5s. 5s2. 3, 4d. 1, 2, 3, 4, 5, 6, 7, 8, 9. But again, S's and D's very close together. And oh, a D9, that's so close to being filled. So instead, again, it will promote one from here and pop it into here. And you're going to end up with 5s1 4d10. Remember months back I told you silver was always a +1 charge? This is why. Because it loses this 1 in the S and has a filled D, and that makes it very stable. So a silver ion is always a +1 because of this tendency of it to move that 1 electron up to the D and fill the D. That's why copper has 2 common ions, 1 and 2, whereas most of the other transition metals don't really have a +1. So a lot of chemical behavior can be traced back to electron configuration, to where on Earth the electrons are and how they arrange themselves. That's why this chapter is so important in understanding how reactions happen.